Hello class, this is Ms. Riggins with today's video on Chapter 3.3, the Product and the Quotient Rule. As you're watching the video, please remember to write down important notes, equations, formulas, or statements, as well as any questions you may have. Feel free to pause, rewind, or even replay the video as often as you need. At the end of the video, please write down the summary and a top question that you have, and then submit those in via the online whisk form. All right, let's begin. The product and the quotient rule. We've been looking at ways to find the derivative of the sum of two functions and the difference of two functions, as well as a scalar multiple of a function. But today we're going to learn about how to find the derivative of two functions that are the results of multiplying each other or dividing each other. Okay, so let's begin. Before we start, we're going to do a little change in the notation. We're going to refer to delta f to be the difference between the f function values and delta g to be the difference between the g function values, where we're assuming that f and g are differentiable functions. So therefore, the derivative of f at x can be defined as a limit as h approaches 0 of delta f over h, and likewise limit as g, the derivative of g prime at x is a limit as h approaches 0 of delta g divided by h. Okay, so it's the same definition. We've just included a new way of noting the numerator difference, which was we're going to call delta f and delta g based off the functions. So let's assume that we have two functions f and g that are differentiable, and if we want to look at the product of their functions to see if they're differentiable. So if I take the derivative of the product of those two functions, it's essentially by the definition of limit, the limit as h approaches 0 of the multiple of the two products evaluated at x plus h, subtracting from the multiple of the products evaluated at x divided by h. Okay, simple enough. So in order to solve this, we need to take a look at this numerator function, which is f of x plus h times g of x plus h minus f of x times g of x. Now, if you recall, f of x, g of x, f of x plus h, and g of x plus h are all function values. So let's say, for example, that I want to describe them geometrically. So let f of x and g of x be the area of a f of x, g of x rectangle, and let f of x plus h times g of x plus h be the area of a f of x plus h by g of x plus h rectangle. So let me show you that picture right here. So as you can see, we have these two rectangles. This is my f of x, g of x rectangle. As you can see, f of x by g of x. And then we have my f of x plus h times g of x plus h rectangle. Here's the length f of x plus h, and here's the width g of x. Oops, sorry. Scroll it down a little bit more. G of x plus h. Okay, so we have this bigger rectangle. And if I take a look at subtracting these two from one another, the result is what's left over in this shaded triangle. Okay, so let me show up here. So f of x plus h times g of x plus h minus f of x times g of x is equal to basically the area of the big rectangle minus the area of the unshaded area. Well, minus unshaded area. And what that is left over is essentially these three shaded rectangles. This one, and this one. Okay? So that's what this difference is equal to. So let's take a look at what that is. I'm going to recall, if you remember, the difference between f of x plus h and f of x is delta f. And the difference between g of x plus h and g of x is g of x, delta g, I'm sorry, delta g. Okay? So that means the area of the three shaded rectangles can be broken up by the area of each particular rectangle. So let's start with delta f by g of x rectangle, which is this one. Okay, Okay, you know I can't draw. And then the next one is the f of x times delta g rectangle, which is this case. Here's my f of x, and here's my delta g rectangle. And of course, what's left over is my delta f delta g rectangle, which is this one right here. Okay, well, let's take a look at these quantities, and it's important to note, just so you can get an idea what these are. So let's take a look at this important quantity right here, so we'll know. Let me try and find a color I have not used. This right here. So let's take a more detailed look at that. So we're going to divide both sides by h, and when we divide both sides by h, then the area of each of those respective triangles looks very similar. So we're going to take a look at each piece right here. So let's look at this first piece right here, the delta f over h times g of x. Let's take this piece as the limit as h goes to 0. Well, if you recall, this piece right here represents the same thing as f prime of x. So really, as limit as h approaches 0 of this piece is essentially f prime of x times g of x, because g of x isn't changing as h approaches 0. Then we take a look at this, the second piece, the second rectangle, f of x times g of h over h, and the limit of that as h approaches 0. And if we put the h underneath the delta g, then this piece looks very much like the limit as h approaches 0 of delta g over h is g prime of x. So this statement right here ends up looking like f of x times g prime of x, because f of x isn't changing as h approaches 0. And then last but not least, so we can see this one right here. A little bit tricky. Well, I'll do this one. This piece right here, as you can see, as the limit as h approaches 0 of delta f over h times delta g over h. Well, what we're going to do is a little trick by multiplying the numerator and the denominator by the same thing. So we're going to multiply the numerator and the denominator by h. And then what this ends up looking like is doing some algebraic manipulation. This right here is f prime of x. This right here is g prime of x. But the limit as h approaches 0 of h is just 0, which means that all of this statement right here will go to 0 as h approaches 0. So in summary, this piece cancels out, and what we're left with once we apply the limit is essentially, since this piece goes away, or the limit is 0, we're left with f prime of x times g of x plus f of x times g prime of x, which in other words, the derivative of the first one times the second one plus the first one times the derivative of the second one. And that's what the product rule. The only requirement for the product rule is that the functions f of x and g of x must be differentiable on the interval that we're considering it. And if that's the case, then that means that the product rule can be written as such or as such, depending on the notation that you choose to use. In other words, the derivative of a product is the derivative of the first times the second plus the first times the derivative of the second. Okay? All right, I know that was a lot, but go back and take a look at it because it really is an algebraic thing to prove. Now let's go look at the quotient rule, which will not be that long of a proof. In fact, the quotient rule is a lot easier because the quotient rule takes advantage of the product rule. So let f of x and g of x be differentiable functions, and let q of x be the quotient function, the result of dividing the two functions. Of course, we're going to assume g of x is not equal 0 at any of the intervals that we're considering, because then the function would not be defined. So if f of x divided by g of x is equal to q of x, then that means f of x is equal to q of x times g of x. And that implies that f prime of x, using the product rule, is q prime of x times g of x plus q of x times g prime of x. This is nothing but the product rule that we just proved. Okay? And if I want to to change q of x into what q of x is equal to, which is f prime of x over g of x, it looks like this. And remember, we're trying to figure out what q prime of x is. We're trying to isolate this, so let's isolate q prime of x. So we subtract from both sides f of x over g of x times g prime of x, and then we divide by g of x to get q prime of x by itself. Doing some algebraic manipulation and simplification, we end up with q prime of x, or the derivative of f of g of x divided by g of x, to be f prime of x minus f of x over g of x times g prime of x over g of x, or which is essentially this. I know this is a lot, but that's okay. But that is what the formula is, and it looks very complicated, but I'm going to show you a shortcut that will make it a lot easier to remember if you like shortcuts. But this is what the statement says. The theorem in the book. Only if f of x and g of x are differentiable on the interval that we're talking about can we divide the two functions together, as long as g of x is not equal to 0 on any of the functions that we're talking about. And you can either use f and g or u and v, depends on how you put it. Now here's a shortcut. So if we consider the numerator function as the high function and the denominator function as the low function, my high school calculus teacher taught me this. The derivative of that quotient function is low d high minus high d low all over low low. Low d high minus high d low all over low low. The low function, which is g, derivative of the high function, f prime, minus the high function, f, times the derivative of the low function, g prime, all divided by the low function squared, low low. We can apply that to up here as well. In this case, b is my low function and u is my high function. So low d high, so low v, derivative of the high, minus high, derivative of the low, all over the low low. So in essence, the derivative of a quotient is the derivative of the numerator times the denominator minus the numerator times the derivative of the denominator all over the denominator squared. Low d high minus high d low all over low low. All right, that's the end of the video, unless you want to see some examples, and then I'll work out some examples for you. Here's an example of using the product rule to find the derivative of a function. So if the function is x squared minus 1 times the quantity x plus 5, the derivative would be the derivative of the first times the second plus the derivative of the second times the first. Of course, order doesn't matter as much because we're doing multiplication and addition, which is associative. And so the derivative of the first of x squared minus 1 is just 2x, and the derivative of x plus 5 is just 1. And so when I substitute those derivative values in, then all I have to do now is just simplify, and I end up with this expression. And of course, we like to keep everything simplified, so this is the final answer. Okay, using a quotient rule, if I have a function here, which is the result of dividing two functions, if you remember, low d high minus high d low all over low low, well, if that's the case, then the derivative of this function is low d high, derivative of the high, so the derivative of 2 sine of x is 2 cosine of x, minus high, 2 sine of x, derivative of the low, derivative of 3x squared minus 5 is 3 times 2x, all over low low, which is 3x squared minus 5 squared. So doing some algebraic simplification, we get over here in the numerator 6x squared cosine x minus 10 cosine x minus 12x sine x over 3x squared minus 5 quantity squared. And that's the simplest as we can go right now. And so that was our function. As long as x cannot be, as long as the denominator 3x squared minus 5 is not 0. Okay, so here's some examples. Now this really is the end. Thanks. Bye-bye.